And so this structure is no-go. Can't do it, even though the formal charges are looking good. And so we're stuck with a formal charge. Well, if we're stuck with a formal charge, which structure do you like better? Do you like structure A better, or do you like structure B better? And why? No ideas?
B.
You like B better? Why?
Oxygen, more electronegative.
Yeah, I like B better. I like B better. Why? Because if there's a tug of war for electrons, this is a tug of war for electrons. It's oxygen versus nitrogen. Who do you think should win? Who gets the negative charge? It would be nitrogen in structure A or oxygen in structure B. The more electronegative you get the charge. And so B should be the most stable. Okay. It's where the negative formal charge goes on the more electronegative oxygen versus the less electronegative nitrogen. In Chem 1A, you're expected not to do everything black and white. So, for example, we have been doing things black and white. You know, which one's more stronger? Well, oxygen is more stronger, and therefore the electron goes there. But now you're expected to put some, qualitative analysis into that, and that is how much stronger is oxygen than nitrogen? Look at the periodic table. Yeah, how much stronger is not much. Because the three most electronegative elements in the periodic table are nitrogen, oxygen, and fluorine. Fluorine's a 4O, oxygen is 3,5, nitrogen is 3O. Those are the three most electronegative elements. Chlorine's also 3O, but chlorine's much bigger. And so a 3,5 versus a 3O, is that a huge difference in electronegativity? Would you say so? Yeah, it's a little different, right? A little bit different. But on the other hand, not so different, right? I mean, we saw something like a 2,5 versus a 2,1. Remember that? What was that 2,5 versus 2,1? Does it ring a bell, those numbers? 2,5 versus a 2,1 electronegativity? The organic chemist is automatic. Boom. Yeah, that's easy. Organic chemists would know because they work with hydrocarbons a lot. And 2,5, 2,1 is hydrocarbon, right? All hydrocarbons are nonpolar. (3,5) versus 3,0 is not a huge difference. And so, yes, oxygen's stronger, but how much stronger? A little bit stronger. A little bit stronger means that this. It means that this is a bit more complicated. Oxygen is a little stronger. Both are highly electronegative. In other words, both have a very strong pull for electrons. Oxygen is a little stronger. Now, if it was one-sided, let's say this was oxygen and this was something like carbon, then forget it. We'd expect just one structure. But what we're going to have are this. We're we're going to have non-equivalent resonance forms. We've seen non-equivalent resonance forms before. That is non-degenerate. You know what degenerate means? Anybody know what degenerate means? There's a common word in chemistry and physics. Degenerate. What does that mean? Somebody remind me. It's a chapter 7 word. Or not chapter 7, sorry, chapter 8. Chapter 8 word. Stanley? No, it doesn't have to do with hydrogen. Kinda. Same energy, right? Same energy. And so earlier when we looked at a bicarbonate, we eliminated one structure. You know, there are 3 structures that we generated, but one was way too high in energy, so it wasn't anything we worry about. In this one, we'd like to eliminate this. Can I eliminate this structure? Just forget that structure. We'll just go with this structure. Is that okay? No, it's not okay. This one, so what we have is, since we have the non-equivalent resonance forms, we have 2 forms that we're going to end up with for this. I'll just write the, and we write the double-headed arrows showing it. The two forms that are going to contribute. Both these forms contribute to the resonance hybrid. This minus this. This was plus minus like this. Both of these will contribute to the resonance hybrid, and so, but this one should be the dominant form, right? And so, you know, let's guess. You know, we could just take a guess. Let's say this one is 80%, and this one's 20%. In other words, this one's, let's say, 80% more stable. If this one's 80% more stable, then this is just an example. This is just a guess. Then the hybrid's going to look something like this. You know, hybrid's a mix, but normally we just do an even mix of all the resonance forms. So if there are 2 resonance forms, we call it a 50-50 mix. If there are 3 resonance forms, then we mix all 3, you know, and so each one contributes 1/3 to the overall hybrid. In this case, we have 2 resonance forms, but it's not going to be a 50-50 mix, you know, like we had with the previous structure. This one's going to be like a 20-80 mix or 80-20 mix. And so if it's like this, then, you know, what we have is we have something like this scenario here. We have a double bond permanently fixed here, okay, like this. Now let's take a look at these extra electrons here. You know, the extra electrons are going to flip, you know, from oxygen here to nitrogen here. It doesn't really flip, it's just spread out. So these extra electrons are spread out between these 2 bonds. And so what we say is it's more concentrated in this bond, you know, 80% more concentrated than this bond here. And so if we've got more electron density over here, then maybe we'll call this not a double bond, but maybe we'll call it a, oops, no, I'm wrong. No, I got it backwards, sorry. I got it backwards. Because it's 80%, the second form, 80% the second form is like the triple bond. And so that means this. It means that these electrons are going to be concentrated here, so like this, and then they spend less time here because that's more like a single bond over on the right side. And so what we'll call this is, we're going to call this a 2.8 bond, and over here we'll call this a 1.2 bond. This is just as an example, you know. I don't know what the split is. We'd have to have some additional data, but you know, we're just taking a guess here. It's better than calling it 50-50. And so a 2.8 and a 1.2. So it's more like the triple bond than a double bond, and this is more like a single bond than a double bond. Now there are going to be two lone pairs, or no, one lone pair fixed on the nitrogen that doesn't change, and two lone pairs fixed on the oxygen. So we got one lone pair fixed here, two lone pairs fixed here, and then we have a lone pair that's spread out over the two. And this lone pair seems to be concentrated more on the oxygen than the nitrogen, because that structure is more stable. And so this is going to be a minus 0.8 charge here. This would be a minus 0.2 charge here. And we know oxygen is more electronegative, so maybe it wins more of the electron density from the nitrogen here. And then the positive charge on nitrogen is fixed at +1. And so this would be a hybrid structure based on non-equivalent resonance forms here, with unequal contributions from the resonance forms. And that's because both these resonance forms are reasonable. Now, if there's a resonance form that's totally unreasonable, like the one we had yesterday, then we just ignore it completely because it should not be a contributor to the hybrid. In reality, it could be a very minor contributor to the hybrid, but it's not worth factoring that in for us here.
What is it, 2.8, 1.2?
The bond. Here, the bond here is a 2 just means double. 3 would be a triple. And so here, the bond here, the nitrogen-nitrogen bond in this resonance form is a double, a 2. And the bond, nitrogen-nitrogen bond here is a triple, is a 3. And so is it 2 or 3? Well, normally, if these were equivalent resonance forms, we just split the difference, right? If these were equivalent resonance forms, we call it 2.5. This is 50-50, right in the middle, right? And then we look at the oxygen. The oxygen is a double bond here and a single bond here. And so if this were 50-50, we just call it 1.5, just, right in the middle. But in reality, it's closer to this. So if it's closer to this, then it's closer to 3 than it is 2. Well, how much closer? Well, it depends on what percent. If we want 90% this, although 90% this would be pushing it because, oxygen isn't that much more powerful than nitrogen. And so maybe it's 70%. Let's go down. Let's go to 70%. Let's do a 30-70 split. If we did a 30-70 split, then it's closer to 3. Well, how much closer? Well, it would be a 2.7, right? Rather than, and then if this were 70%, then this would be a 1.3, closer to single than a double. Right? And then the charge here, well, this would be a minus 0.7, This would be a minus 0.3 nitrogen. And so it depends on how we do this, the percentage split, and that's why I got this, for that, the numbers here. And these numbers are just guesstimates, estimations. Actually, we could look it up because somebody's done it, There's different ways you could do this. Why we're doing this is we just want to figure out what the maximum amount of information we can do without doing hard calculations, without doing too much theory, right? This is very easy stuff compared to actually having to do the theoretical analysis of this. Now, if somebody does that and gets a number, and then those numbers come way up, well, they could very well be these are just the simple charges. Unfortunately, the data's not there. It's there somewhere, but you know, this one's not bad because this one, when I say doing the hard calculations is if you're working with a calculator and pencil and paper. But you could do hard calculations. If you buy a $5,000 piece of software, then the $5,000 piece of software can do the calculations easily for you. Well, we have $5,000 piece of software that you can do these calculations very quickly. And we're going to do these calculations in the computer lab using something called Spartan. You know. So if you wanted, somebody asked, they wanted to buy their personal copy, so I looked at the price, and it's expensive for Spartan. Spartan's used to do these quantum mechanical calculations, figure out the charge. You know, what is the charge on the atoms? You know, they're going to react, kind of stuff. And so we'll do it and then compare what that. But you'd think they'd have it here. No, probably they don't have it here because it's too much. Well, nitrous oxide, of course, has a lot of uses here. But here they're showing the resonance forms here. But, you know, you got to remember these are non-equivalent resonance forms. One of the things that people do is they look at the bond length. The bond length can tell you a lot, you know, because the triple bond has a certain length. Double bond is a little longer. Single bond's the longest. Double bond's shorter, triple bond's shortest. And so based on bond length, they can tell, you know, about where is it? Is it a double, or is it a triple, or is it somewhere between? Well, it's somewhere between. Is this a single or double or somewhere between? Well, it's somewhere between. And from where it is between, they can estimate. You know, it's not that hard to estimate. Does nitrous oxide burn? What do you think? Will nitrous oxide burn? You know, I don't know if you heard, a lot of people hook up like, I guess, nitrous tanks to their automobiles to make them go fast. Have you heard of that? Yeah, it burns. It burns a certain way to get more. And so, applications. If you look at the applications for nitrous oxide, this is a little small. Blow it up there. Rocket motors. Well, what do you use in rocket motors? They use it as a fuel or an oxidizer. Actually, nitrous oxide could be both. It could be both a fuel and oxidizer because it's +1, so it could lose electrons or it could gain electrons, right? And so it could be either a fuel or an oxidizer. I kind of wonder how they're using it in rocket motors. Internal combustion engines, aerosol, propellant, medicine, recreational use. I think the recreational use is illegal. Rocket. Let's see. Nitrous oxide can be used as an oxidizer. In a rocket motor. This has the advantages over other oxidizers in that it is not only non-toxic, but also due to its stability at room temperature, easy to store and relatively safe to carry on a flight. As a secondary benefit, it can be readily decomposed to form breathing air. Oh, I didn't know that. So I guess nitrous oxide, if it decomposes, it forms nitrogen and oxygen in a redox decomposition. The nitrogen and oxygen is air. High density and low storage pressure enable it to be highly competitive with stored high pressure gas systems. And that's interesting. Let's see an automobile engine. In vehicle racing, nitrous oxide allows the engine to burn more fuel by providing more oxygen than air alone. Oh. So it's just like adding more. I guess you could have a bottle of O2, but maybe O2s do the same thing. resulting in more powerful combustion. The gas itself is not flammable at low pressure and temperature. So this gas is hard to burn. But you notice they say at low pressure and temperature. At high temperature, I'm sure it's flammable. But it delivers more oxygen than atmospheric air by breaking down at elevated temperature. Therefore, it is often mixed with another fuel that is easier to deflagrate. Deflagrate is like decompose kind of explosively. The nitrous oxide is stored as a compressed liquid. Oh, that's good. Oxygen wouldn't. And so it's primarily used as an oxidizer. Nitrous oxide is approved for use as a food additive, as an aerosol spray propellant, whipped cream, canisters, cooking sprays. Also to inhibit bacterial growth in potato chips. So a lot about nitrous. Nitrous oxide has been used as an anesthesia in dentistry since December 1844. This type of information, you know, just general information in a report would go in what section? This would go in the intro section of a report. So if you find interesting stuff about sulfate, you know, you could share it with the reader. Some recreational use. Nitric oxide is pretty interesting. NO. Nitric oxide won Science's Molecule of the Year maybe 10 years ago. You wouldn't think so. NO, why would that be Molecule of the Year? I mean, it's been known, it's been well known for a long time, and NO's not non-toxic. NO's more toxic. You know. But you could read about it on Wikipedia, sure. All right, so now we know a little bit about the structure, but you know, this doesn't really dig into the, Wikipedia doesn't really dig into the structure of this. Some synthesis. History. Wow. Very thorough, but double ionization. Well, this is something we'll do in lab. It's not hard. You know, it looks like most of these are reactions, nitrous oxide, so skip those. So keep this in mind. We said an 80-20 split. Let's do some quantum mechanical calculations and see, you know, what kind of charge we generate on these. Which form is more dominant by how much. All right, that's resonance forms. Now we're going to talk about structure. Using VSEPR. VSEPR stands for valence shell electron pair repulsions, and we're just looking at groups of electrons. You know, and the first thing is we need to determine groups of electrons. As far as groups of electrons, we have different groups. This would be just a single electron. You know. A single electron, when you have a single electron, what's it called? This always happens when you end up with an odd number of electrons. When you have an odd number of electrons, one electron is going to lose out, and that one electron creates something called a free radical. Okay. This is a free radical. And the single electron in VSEPR, you know, there's space requirements. You know, it's still negative charge density. The electron cloud. The electron cloud's going to take up some space. Get some space requirements like this. If we have a lone pair of electrons, a lone pair of electrons are going to have two electrons there. The lone pair. And this is going to take up more space because, you know, you got more electron density there, so it takes up more room. You know, so it needs more space. And in VSEPR, we're looking at this type of space. Then we have a single bond. You know, a single bond to, let's say, B here. If we have a single bond, you know, this looks weird. But a single bond, does it take up more space or take up less space? Well, it turns out it takes up less space on atom A because some of the electron cloud is being pulled towards atom B. And so now the atom B is sucking some electron density, so all the electron density isn't concentrated on A, so it ends up taking less space. When we have a double bond, you know, a double bond takes up about as much space as a lone pair on atom A. You know. We've got more electrons there. This is all from atom A's perspective. Then we have a triple bond. Triple bonds are even shorter than double bonds. Triple bonds are going to take up a lot of space, more space than a double bond. And so when we have these groups of electrons, you know, they take up a certain amount of space. They need their breathing room. And so this is going to dictate how the structures will arrange themselves because we try to minimize the repulsions. We're looking at repulsions between groups. And so VSEPR is looking at repulsions between groups to arrange the three-dimensional structure. And so we have different ones like BEF2. BF2, does this look right? Well, beryllium doesn't have an octet, right? We can make beryllium have an octet. It's pretty easy. Create a double bond here. Create a double bond here. Now beryllium has an octet. Does this structure look good? Well, it looks very bad. This structure looks very bad. Does somebody know why? This structure looks awful because of the formal charges. The formal charge on fluorine's plus, and we got a -2 formal charge, beryllium. This structure looks much better because everybody has a 0 formal charge, but it looks bad because of the lack of the octet. And so here we have to use some memorization to figure this out. In this case, what is more important? Getting the octet or screwing up the formal charge? Well, you have to look at how screwed up the formal charge is, and just how screwed up is the formal charge in this particular structure. Well, one, you know, it's kind of high, beryllium, and when you get -2 or +2, those are high formal charges. It would be very unusual sometimes to have. And so in this particular structure, what's bad about it? What's bad about it is you look at it, basically beryllium has taken 2 electrons. Well, who did it take it, or whom did it take it from, you know? Well, actually, one fluorine and another fluorine. And so is beryllium going to be able to attack two fluorines and pull off an electron from each of them? Well, let's take a look at the electronegativity. What is electronegativity of beryllium compared to fluorine? Fluorine has electronegativity 4.0. You look at beryllium. Beryllium's electronegativity is way lower. Beryllium, in fact, is a metal. All metals have very low electronegativities because they're, except, well, beryllium's electronegativity isn't terribly low, but because it's quite small. But basically, the rule that you memorize is that fluorine will never form more than one bond. Fluorine never forms more than one bond because it's the most electronegative. And in order to form more than one bond, it has to lose electrons. And fluorine's not going to lose any electrons. And so this is very bad because fluorine is not going to lose electrons to beryllium especially. And so we're stuck with less than an octet. Well, when we look at this, we have two single bond groups. And two single bond groups would like to arrange in a linear fashion. And so when we look at the groups, we have something called a group geometry or electron pair geometry. And so I'll call it that. It's a group geometry or electron pair, but it's not literally a pair of electrons. It's just called electron pair geometry. So if we have an atom like this, then if there are only two groups here, they'll want to separate from each other as far apart as possible. And we end up with linear. When we end up with linear, then we have something called molecular geometry. And so it goes in this order. We have to first figure out the group geometry and then the molecular geometry. Molecular geometry is going to be the geometry of the bonded atoms. So we could have something like this. We could have something like this. We could have something like this. Two singles, two doubles, or something like this. A lone pair, maybe even a radical. These are all going to be linear. Molecular geometry. So molecular geometry is the geometry of the bonds. Geometry of the bonds. Well, this is not really the bonds here. This is not a bond. This is not a bond here. So typically we look at these here. Although this is still going to be linear. So let's do them all really quick and then break. Okay, the next is if we have three groups. If we have three groups, then they'll want to separate as far apart as possible. And to separate as far apart as possible, we're going to get this kind of geometry, which is called trigonal planar, in which the groups are separated by an angle of 120 degrees. Then we look at the molecular geometries that are possible with this. And so we're going to have, these. Like we could have double bond here, two singles, or etc. These are going to be trigonal planar arrangement of bonds. But if we have a lone pair in there, so for example, one of the groups is lone pair and we have two bonds like this, or we have a lone pair like this and maybe a double bond like this, right? Then we call this angular or bent. And the ideal angle is 120 degrees because there's another angular or bent. There's a 109 degree angle. So we have to distinguish between the two angular bends, the 120 or the 109. If we have four groups, the fourth group we can just put on the top. If we put the fourth group on the top, it's going to push these three down, and it's going to make the classic tetrahedral shape. For the tetrahedral, we're going to draw it like this. We're going to draw two of them in the plane, and so these two groups are separated at an angle of 109.5 degrees. And then this one's going to come out of the plane here. And so this one's going to be separated at 109.5, and then this one's going to be going in. So there's actually four groups here, all at angles of 109.5 degrees here. Okay, and so we call this the tetrahedral. Tetrahedral is spherically symmetric. That is, if you were stuck in a ball inside of the sphere, you'd probably kick out, your legs out like this and your arms out like that or something. Form a tetrahedral. One leg forward, one leg back, and then your arms, left and right. That would be tetrahedral. As far as that's a group geometry, but as far as the molecular geometries go, we look at how the bonds are arranged in that. And so if we have four single bonds, we write them like this. We could have a double bond too. We'll throw in a double bond and three single bonds. And that happens. This would be an expanded octet. This would be tetrahedral as well. Tetrahedral. But sometimes we don't, like in ammonia. In ammonia, we have one lone pair and three hydrogens. This would be like ammonia. This would be, or sometimes we could even throw in a double, throw in a double. So we have three groups, a double and two singles, and a lone pair, actually four groups. So it's still tetrahedral. But when we look at the bonded atoms, the bonded atoms are going to form a trigonal pyramidal arrangement. Trigonal pyramidal. Do these look familiar? Okay, so what we're going to do is we'll take a break, and then we're going to get the model kits, and then we'll build models of these, and then continue on with the rest of the geometries.